Okay, this is a lecture on a molarity of a solution. Molarity is a concentration unit of moles per liter. There are other concentration units that we'll discuss later in chapter 3.4. Now, one thing you have to remember, solutions are made of a mixture of compounds that are uniformly mixed, and we call them homogeneous mixture. There are many compounds in this solution, and we could further define this as a solute and solvent. The solvent is the compound that is in largest amount, and the solute is the other components. It could be more than one. So, for example, sodium chloride in water would be considered, sodium chloride would be the solute, water will be the solvent. The solvent is normally the substance in largest amount, usually like water, usually it would be water. And we call this an aqueous chemistry, aqueous, it was called an aqueous solution. Sometimes you'll find that you get 90% ethanol in water. So for example, 90 grams of ethanol in 10 grams of water. You think that ethanol should be the solvent, but it's the water that dilutes. You add water to dilute the ethanol down to a lower concentration. And that's why we have dilute and concentrated. Dilute is low concentration, concentrated is high concentration. You may have heard these terms already. So let's put a number to this. It's called quantification. Quantify is putting a number on these concentration of moles per liter. So there are many different units. The most common one that we use is molarity. The molarity is the mole of solutes over 1 liter of solution. And you have to remember that a solution is made of the solute and the solvent. So that means that, for example, if we dissolve 5 grams of sodium chloride in 100 milliliters of water, the volume of solution would actually be higher than the 100 mils. Or in other words, we dissolve 5 grams of sodium chloride, then in order to make up the 1 liter of solution, you have to basically put in 995 grams of water. Because remember, the solution is made of solvent plus the solute. Let's take a look at one example determining concentration of solute. You got 17 grams of sodium chloride is dissolved in water, and what we say, we dissolve it enough water to make a total volume of solution that is 1 liter, 1 liter of solution. So the concentration of NaCl, what we have here is a little table. I like to tabulate all my data. We have our mass of sodium chloride, 17.0 grams. The molar mass, if you remember from the previous section on finding molar masses, use the periodic table. So in the periodic table, what we got here, if I could pull this over, no, can't pull this over. Doesn't want me to pull over this. Okay, I'm just gonna pause. Here's my periodic table. I'm just gonna expand the view of the periodic table. Okay, so if you take a look at the periodic table, you basically have the two sets of numbers. This is number of protons. This is the average atomic mass, where by taking the sodium, one sodium, we use this number of 22.99, or you could say 23.0, and chlorine is over here. Now, I understand that for me, it's easy to identify where the elements are in the periodic table. It might take a little bit of time for you to do this. So sodium and chlorine would be 35.45, or you could say 35.5, plus the 23 is that 58.5 grams per mole in 1 mole of the compound. Okay, so 58.45 or 58.5 grams over the moles. In order to calculate the moles, all we have to do is take the number 17 grams times 1 mole over 58.45 grams. Let's do this calculation. Okay, the calculation here is mole sodium chloride is you got 17 grams of NaCl, and what I got here is our fraction. I like to use my fraction right there. You could do this, set this up on your Word PC or the um, Apple computer. Okay, so you got 1 mole of NaCl, and what we want is the 58.45 or 58.5 grams of sodium chloride. And this is how I would set up this equation, because then you could have the units cancel, grams cancel, and you get the moles. And if you use your calculator, it would be 0.291 mole of sodium chloride. And this is what we have. Now the concentration will be 0.291 moles of sodium chloride divided by the 1 liter of solution. That's why we get this. That's why I really like this table right here. I put it together a table so that makes it nice and easy to keep track of your data. Okay, the next example is a solution was prepared consisting of 2 grams, 2.00 grams of potassium hydroxide dissolved in water to make 50 mils of solution. Now let's take a look at this. What we have is 2 grams times 1 mole divided by 56.1. So in other words, what we could do is take the mass and divide by the molar mass to give you the mole. And once you get the mole, you divide by 0.0500 liter solution to give you a value of 0.714 moles per liter, or big M. Now notice that there's only 3 sig figs here. That's because of our 3 sig figs in 2 grams. Okay, so 3 sig figs right here, moles potassium hydroxide, 4 sig figs in liters of solution, but at the end, we go with the lowest number of sig figs, which is 3, and that's 3 for our final answer. The next is, we could determine any of these variables from the concentration. You got volume, mole, or mass. There are 3 variables here. Now, in order to determine any of these variables from the concentration, volume, mole, mass, we could make advantage of this little triangle. And you could see that in the triangle you have moles over liters is moles per liter. So that moles over liters, so moles divided by liters equals moles per liter. You multiply liters by moles per liter. This will give you the moles because the liters will cancel. If you take moles over moles per liter, this will give you the liters. In other words, we take moles times liters over moles gives you liters. So this triangle is quite useful, and you can remember how to apply it or how to construct it, because you're going to take moles over liters times moles per liter. So let's take a look at an example. Calculate the mole of HCl that is present in 25 milliliters of 0.975 moles per liter HCl. We'll expand this to moles over liters, and we have to multiply the volume. So in order to multiply the volume by the concentration, you'll end up with with the answer. But note right here, if we got 25 mils, the units don't cancel, but we need one more factor, is the magnitude factor. So milliliter, 1 liter over 1,000 milliliters, you could cancel the milliliters, and then multiply the terms out to give you a value of 0.0244 mole HCl. Using the triangle will be great because you know that you multiply the volume with the concentration. Liters times moles per liter gives you the moles. But you have to remember that by writing this out along this kind of linear path, you know that units have to cancel. So now we could find grams. We could use the molar mass of HCl and the mole relationship. So remember, a moles times 1 mole of HCl over, so if you take a look at this equation, you'll notice that the units don't cancel. And because the units don't cancel, you have to go back and determine the conversion factor. And the conversion factor should be moles over the grams per mole will give you the grams. And so moles times 36.45 grams over 1 mole, the moles will cancel. Well, you take a look at these other example 2, write out the concentration M fully in terms of point whatever the number is over the moles per liter of solution. Then when you have the grams, you could then find the moles. So, okay, here's a challenging question. How would you prepare 500 mils of aqueous solution of 0.8 moles per liter calcium hydroxide? This is kind of tough, but we'll write out the value of M, which is moles per liter. So the compound, I put this in the table, calcium hydroxide, you have the molar mass of calcium hydroxide because molar mass is where you have grams per mole, will help you convert moles into grams. Okay, concentration, we wrote it full right here is 0.8 moles of calcium hydroxide in 1 liter of solution. The volume that we want is 500 mils, so here's 500. We could write that as 0.5000 liters. So finding the moles of calcium hydroxide, you take 500 mils times our conversion of 1 liter over 1,000 mils, brings it to a liter. That allows us to calculate our mole of calcium hydroxide. Once you find the mole of calcium hydroxide, then what we could do is multiply it by the grams per mole to get the grams of calcium hydroxide required. Then to provide the statement, we're going to say the 2.96 grams of calcium hydroxide is measured and then dissolved in water to make a solution volume of 500 mils. Not 500 mils of water, but a solution volume that involves having the solute and the solvent together, totaling 500 mils. The next unit is dilution of solutions. What we want to do is we want to take a concentrated solution and make it into a lower concentration solution. The concentration of the solution is going to be reduced by adding water, and we're going to do this scientifically and methodically. So the purpose of dilution is manifold, and you could read this, that one example is a parent, you don't want to give a baby a concentrated apple juice, so you add water so that the baby could have a less sweeter apple juice. In microbiology, we need to take a bacteria sample, and we want to count the number of bacterial colonies, we don't want to do it concentrated. We want to do it more dilute, like a dilution factor of uh, 20,000 to 30,000, maybe 100,000. And then what we could do is we could then grow the culture and then count the number of bacteria. Let's do this in chemistry. Here are some keywords. And some keywords are stock solution, pipette, volumetric flask, and aliquot that you'll see in the common laboratory techniques. A stock solution is one that is a known concentration, is the highest concentration of a solution, and it's called stock because we could then have it stored on a shelf. So pipettes, here are the pipettes. There are different sizes pipettes. They could be 25 mil pipettes. This will be a 10 mil pipette or 5 mil or even a 2 mil pipette. And one pipette that has a total volume of 10 and has graduation marks. The most accurate ones are these ones with bulbs. And you can see what I have here is maybe a little Giphy animation I created. And it's basically, here's a pipette going into you're just drawing up a solution, and we're going to measure the solution accurately. And what's supposed to happen is we're emptying out some of it so that that pipette has a marking. You gotta get to that marking. And then we'll deliver that rest of the volume into this volumetric flask. So this is a volumetric flask. And what we do here is the okay, so what we have here is a this beaker has what we call the stock solution. And then we're going to transfer 10 mils of this stock solution into the volumetric flask. So once we transfer into the volumetric flask, we're going to add water. See this line right here? This represents exactly 100.0 mils, and we want to have it so that the curvature of water just sits on top of this line. This curvature is called the meniscus, and this will allow you to have exactly 100.0 mils. So the pipette in the animated film is taking a small amount from the larger amount. That's called an aliquot. It's a small but accurate volume of solution that is obtained from the stock solution. So the concept is really simple. If we took 10 mils of aliquot from a 0.500 moles per liter sodium chloride stock solution and then made it up to 100 mils with water, enough water to make it up to the mark, we could calculate the diluted concentration. And I put a table here. I got C1 is the original stock solution concentration. V1 is equal to the amount, the aliquot that was removed. C2 will be unknown, and we're going to determine that. Volume 2, the total volume is 100 mils. So what we have here is a calculation, a formula that you could memorize. C1 V1 is equal to C2 V2. Basically, C1 times V1 is equal to the mole. And the mole transferred from the stock solution to the volumetric flask remains constant. Only thing that's different is the volume. And so rearrange this to isolate C2 by dividing both sides by V2. And so we get C1 V1 over V2 is equal to C2. Putting the numbers in, making sure the units cancel. So mils and mils cancel. We get 0.0500 moles per liter. The dilution factor, and this can be determined two ways. How much we diluted the stock concentration by. That's what we want to know. And it's determined by either taking the ratio volumes, so the total volume over the aliquot volume, or the high number over the low number in volume. This is 100 over 10, so this is a 10 times dilution. Alternatively, the ratio of concentrations, high concentration over low concentration, gives you a 10 times dilution. Okay, so what you have seen here is a tenfold dilution, and a tenfold dilution is a one-step dilution where we take 10 mils and of an aliquot and make it up into 100 mils of solution. We could also do other kinds of dilutions, like what we call a twofold dilution. We take something like 50 mils of the stock solution and dilute it with another 50 mils of water. So there'll be a twofold dilution. So the high concentration would be 0.5, and we take the low concentration will be 0.25, that'll be a twofold dilution. We could do a 5-fold, 10-fold, 100-fold dilution, or 1 ml of aliquot in 100 ml of solution. So twofold 50 ml aliquot dilute to 100 ml, or 5-fold dilution is 20 ml aliquot dilute to 100 ml solution, and so on. But how about if we have 100-fold dilution or a 1,000,000-fold dilution? That's very necessary, especially in things like biochemistry or microbiology, where, again, if you try to count the number of bacterial colonies that are present, it's going to be impossible if we have a concentrated sample. So we have to dilute the sample in order to grow the colonies and then count it and backtrack it to our original count. So the serial dilution is what we're going to have to use. We don't have a big enough flask to take 1 ml of stock solution and dilute it with 100,000 milliliters of solution. That will be a really insane flask to have. So serial dilution is what we use to accomplish this. Okay, here's a sample exercise on serial dilution. What is the dilution factor as required to prepare 2.50 times 10 to the minus 6 moles per liter barium chloride from 0.500 moles per liter barium chloride? So you take the high concentration, divide by low concentration, you'll find that the dilution is required is 200,000 fold dilution. You can't accomplish this in one step, because in one step you need 1 milliliter and 200,000 milliliters of solution, or of water plus the diluted aliquot, to dilute the aliquot. So the process, what we could do is we could do a serial dilution that requires a 20-fold times 100-fold times 100-fold. That'll give us our 200,000-fold dilution. In any order, you could go 100, 20, 100, or 100, 120, doesn't really matter. Or you could do a 20 times 10 times 10 times 100. This will give us our 200,000. Or we could do it 20 times 4 tens dilution. The process is very simple. All we have to do is get a beaker, transfer our stock solution into this. Then what we're going to do is we're going to pipette. We're going to remove exactly 5 mils of the stock solution, transfer it into a clean volumetric flask that's 100 ml. And then once it's transferred, we're going to add water. That's enough water to make up 100 ml solution. And there will be a line right here where we could touch the meniscus. The meniscus just touches the line. Then we cap this, shake it up, mix it up thoroughly, and then take a clean pipette. You take another 1 ml with a clean pipette, transfer it to a clean volumetric flask that's 100 mils. Again, add water to the meniscus, and then cap it, shake it. Then what we're going to do is take another clean pipette, transfer 1 ml from this second flask to a third clean flask, and then make it up with water to the meniscus, cap it, shake it, and now we have a 200-fold dilution. Our solution will be 200-fold diluted, 200,000-fold diluted. And this is the description right here. The dilution factor is always given by the high concentration or low concentration. And you guys could try these other ones right here. These are the other dilution calculations. And dilution calculation answers is given right here. If you have any problems with this, please consult with me. And this is also some videos on dilutions.